there's a little bit of background noise here because they're doing some work, but that should be over pretty soon. But let's see here. Are there? I don't see any questions yet. So, okay. So today what we're going to do is we're going to try to finish up. We're definitely going to finish up relational algebra, and we're going to try to kind of finish up the bulk of SQL, if not all of SQL, at least for this stage of the course. So let's go back to let's just finish up the relational algebra here. I'm assuming people can see this pretty well. I can make adjustments. I want to cover the division operator because that's going to come up in recitation as well. So let's assume that what we have here is we have, let's say, the restaurants. And let's see if people see that. And we have, let's say, the name of the restaurant and the city. And then we have eaten at, and we have like the, well, we'll say basically the person and the restaurant. Okay, so this right here, this restaurant here, that's going to be a foreign key into the name here for the restaurant. And let's just give this a state. So can people give me some feedback here if everybody can see this well enough? Good. Okay, so let's give this a little bit of a state here. So let's just say that the state of this one here, and when I say state, I mean like an actual table. So this might be something like, I hope people can hear this, something like Rex Umio, and let's say, for instance, Rex Umio, and let's say Pipes. I guess that's a restaurant. Umio, and let's say Taco Bar Stockholm. Okay, then we have that, and then let's say we have Mike, Rex, Mike, Pipes, Dave, Rex, and then of course there could be more data here. So if we want to basically say give the person who's eaten at every restaurant in Umeå, then let's talk about how we actually go and we compute that using the divide operator. Okay, so again, I hope that people understand what we're going after here. We're going after the people who've eaten at every restaurant in Umeå, and as we can see here, that should be Mike here, because the only two restaurants in Umeå are Rex and Pipes, and Mike is eaten in both of those. All right, so I hope that's clear what we're going after here. So if we just go to the relational algebra, to the definition of the divide operator, it's very simple to how we wind up doing this. What we wind up doing is we all we do is basically say that it's going to be restaurants divided by, and then I have to project. Oh, I'm sorry. It's eaten at divided by, and then what I have to do here is I have to project the name, and I have to select for city equals Umeå over restaurants. People see that. Okay. So what does that give us then? This returns a table here, and the table that it returns here is simply going to be, if we go back to that database state we had before, it's going to simply be Rex and Pipes. And of course, the eatnet here is Mike, Rex, Mike, Pipes, Dave, Rex. Okay. And then it's well, okay, actually, I'm sorry, I made a slight mistake here, and I'll just use an extended projection here. Restaurant, because the names actually have to match up here. So we have restaurant, and I'm just using an arrow here to do the renaming. Restaurant, and then we have a person, restaurant. Okay, and as you can see here, then it's Mike is what's going to come through here. So what this actually equals, this will actually wind up equaling Mike. Okay, we're doing this under a set semantics, so we don't have any. I think they might have gone now. We're doing this under set semantics, so we don't have any duplicates there. Okay, so that's I hope that everybody follows that. Okay, so what would be a problem if I mean there is still a lot of places that could go wrong here. If you don't do the projection or the renaming here, you can get into trouble. But let's just focus on this right here, and wait, let's try to kind of get to the bottom of what this really means. I mean, hopefully you understand what it means in terms of like what it's after. But what is it really? What is this? This divide thing? It's like kind of like, okay, if you say so, but what's really going on with divide here? Let's kind of delve into that, and let's look first of all. Let's look at the definition of what divide means. So this is what the divide actually means. Now, X right here represents a set of attributes. Okay, so if we go back into here, if we go back into like the R is going to represent kind of eat but here the set of attributes would be person and restaurant. Okay. So R over a set of attributes X divided by S over a set of attributes Y, what that winds up equaling, and just bear with me here, it's project X minus Y over R minus project X minus Y over project X minus Y here, R Cartesian S minus R. Okay. Sadly, I wasn't able to kind of cover that whole thing here. Oh, let's see if this chat scrolled here. Okay. Okay, so this is the actual definition. So when we actually go into what this division operator is, this is actually its formal mathematical definition. So let's try to get some intuition around about what's going on here with R. So in our example that we had before, R is restaurants, and I'm sorry, R is eat net, and S is restaurant. Okay. If I do the following, I have to kind of make sure that we get the what we want to do is we want to get how am I going to do this? All right. So let's simplify the problem just a little bit, just to kind of make it so we can really kind of fully understand this, what's really going on here. So I'm going to basically say that R is going to wind up being it's a relation for person and restaurant, and then S is just going to be restaurant. So I've done the renamings here, and I've also clipped out the city, which is going to be restaurant, which is going to make it kind of make it simpler. Okay, so let's go. Let's grind through what this actually means here. So that means what X equals, it equals person and restaurant. Okay, and what Y equals in this definition up here is that just equals restaurant. So let's unfold this, and let's kind of let's do the example here. Let's actually show what this actually does. Wait, almost out of paper. Okay, so if we go over R, which is the eaten at, what this is going to wind up giving us, this is the person and the restaurant. I'm sorry, this is person and restaurant, and this is just the restaurant. So this will just give us person. So that'll basically be project person over this R we have. Okay, so that'll actually wind up just being Mike and Dave. Right? That's what this piece right here equals. Okay, and that's going to be minus, and then it's going to be project person. And this is where it kind of gets kind of interesting. So what this is going to wind up doing is this is going to wind up basically saying the what we want to do is we want to do a Cartesian product between our eaten at and I'm sorry, our eating at and our restaurants. And so what that winds up giving us is the following. This Cartesian product here, what we're going to see here is we're going to have Mike, Rex, Mike, Pipes. I'm sorry, Dave, Rex, and I should just do this right here. So sorry, the sound is back now here. So I made it slightly, okay, so X minus Y here. So what this is going to do, this right here, this little piece right here gives us Mike and Dave. And then we're going to do a Cartesian product with S, which is just the restaurants. So that gives us Mike Rex, Mike Pipes, Dave Rex, Dave Pipes, right? And then from that, we're going to actually subtract out the actual state of the relation. And the state of the relation, if you recall, was Mike Rex, Mike Pipes. Hope you guys can still see this. Dave, I think it was just Rex. He had just eaten at Rex. Okay, so this is all the possible combinations, right? These are all the possible combinations of the names of the people paired with the let's see. Okay, the brackets are matching up. Basically, the projection here is over R here. It's just X minus Y over R. Let's see if I can get rid of some other. And then, so this is just pulling out all the names that are coming in from the R, all the names that are coming in from the visits relation, getting all the different names there, Mike and Dave in this case here. And then what it's doing is just taking those and it's just doing a Cartesian product with all the restaurants. Okay, so that's just giving us the full set of combinations here. And then what we do is we actually take in what we actually have represented in the table. And what that does is that basically makes everything drop out of this except for what isn't true. And that is Dave eating at Pipes. Okay, so this survives this subtraction here, Dave eating at Pipes, because it didn't happen, right? And then this is basically, but this is evidence, or this is a proof that Dave does not qualify for having eaten at every restaurant, because something in the Cartesian product, well, it didn't get subtracted out. If Dave also ate at Pipes, then there would be no Dave tuple here, right? Then Dave would also qualify as being a person who ate at every restaurant, but he isn't. Okay, so what this does right here is this basically just gives us out. Basically, it just gives us out this table here, and then we project Dave from that. So what we do is we wind up getting Dave here as that person, and then since these are being minused, then what's left over is Mike. Right? So the result of all this is Mike. All right? So that's exactly what's going on inside the division. That's the exact definition or mechanics of how division is operating. Okay? So I hope that makes sense to people. And let me know if there's any questions. But basically, you can trace it back to this definition right here. So this will be useful here in the recitation. Okay, it looks like I need to go and fetch more paper. Let's see here. No, actually, I have some paper. Okay, so I don't see any questions coming up. There might be an issue of the following. But let's just talk about some of the practicalities here, though. If I do the following, if I say, okay, like if we look at this definition here, what happens if these if I wind up saying something like this? I say let me see here, x minus y, x minus y. So if I say something like the following, I say I mean, where can things go wrong? We'll cross that bridge when we come to it. I think this is probably good enough to kind of keep things here. This is I think you have enough to kind of work with to maybe get a full understanding of what division is doing. Okay, so let's go on to another issue that I wanted to cover before we go on to more SQL, and that is I wanted to talk about outer joins. So so if we have let's say that, for instance, what we have is we have and the outer joins we do in relational algebra or extended relational algebra are going to be ones where we it's kind of a form of a natural join. So let's say that we have this. We have R, and R is has the attributes A and B, and then we have S, and it has the attribute B and C. Okay, and this has 1, 1, and this has 1, 7, and this has 1, 4. Okay, so the question might be this: it's like, what is, and let me put another one here, 2, 7. Okay, so what is our natural join S? I hope people can. This, I hope that people can kind of give me what that is. Right? I mean, what does that wind up equaling? Well, it's a natural join. So the attribute it's going to do the natural join on is the B attribute. So really, actually, it winds up just being 1, 1, 4. A, B, C. Right? That is the natural join between these. Now, as it turns out, a lot of times you don't in a practical setting. What you want to do is you want to actually have it so that you want to have these things. If things don't match, you still want to have them report. So if we do the following, if we do what's called an outer join, R outer join S, what that winds up equaling is it says the following. It says, okay, 1, 1, all right, 1, 1, 4. That makes it in because this matches right there. And then 1, 1. Okay, this 1, 1 made it through. So this is fine, and this is fine. They both kind of are making it into the join result. But now we have 1, 7, but 7 doesn't join with anybody. So the idea behind an outer join is you'll say 1, 7, and then null. Okay? So these other ones that didn't match still hang around in the answer set. And it also works on the other side as well. So, I'm sorry, null 2, 7. Okay, sorry, that's another very pretty null. Okay. All right. So what just happened? What's happening here with this notion of an outer join? All that's happening is basically saying that if something doesn't join through, if one of the tuples in R doesn't join through, then just pad it to the end, just put it on the end, put it in the result, and then pad it with nulls. Okay, so that at least it survives the at least it's not disappearing. So very often, I mean, people, this is very, very practical. So, and the reason why is because sometimes it might be that you want to have a record inside the join of what didn't match. Like, for instance, let's say that you're looking for, you think that you have, like, well, we've matched all these particular companies to these particular customers here, but we couldn't match this particular company to any customers, but we still want the company to be around so that we at least know that we didn't make the match, right? So that's it comes up quite often. It's in fact, I mean, I think many well, I mean, I don't know what proportion of joins in the real world are outer joins, but generally it's used quite a bit. Now the thing is that you can actually do outer join by, it is just syntactic sugar. Okay, it is just syntactic sugar. So you can do some operations where you can determine what doesn't join through, and you can then do unions, and you can build up something that's equivalent to an outer join. But the key point about the extended relational algebra and outer joins is that outer joins are, if the query processor knows doing an outer join, you can do it much more efficiently if it's labeled as an outer join. Okay, so it is just syntactic sugar, but it's also very practical in the sense that it helps efficiency. Okay, now there's some other variants of this. So you might think, hey, there's what's called a left outer join, which means that we're only going to be doing we're only going to do the null padding for tuples on the left of the operation. So that means that this one would not make it through. Okay, so we would not have. So basically, what we'd be doing here, left means that, okay, the left part of the operation is what we're going to do the outer join on. So if 1,7 doesn't match something, then it gets in here with a padded null. Okay, but we don't do it the opposite direction as well. So left outer joins are actually your most common form of outer join. All right, that's usually how you do it. You do a left outer join. So basically, the way the syntax works is you have left outer join, you have right outer join, which is just an analogous thing. It always has to have the O up here. And then if there's nothing there, it's just a full outer join. Now, in relational algebra, we also have the kind of these are natural in the sense that there has to be an attribute that's the same name. In SQL, of course, we're going to see that we have a theta syntax to handle outer joins. Okay. All right. So I hope that was somewhat clear. All right. Now let's go. Let me switch over here now, and let's go to. Excuse me. Let's do a little more SQL here. Okay. So what I want to do now is I'm going to cover this first in the slides, and then we're going to play around with it actually in a actual terminal. But let's just cover it first in the slides, and then we'll go to the terminal. Okay, so let's view a slideshow here, and then let me go back. One second. I have to actually do this in a different direction here, so I'll share the screen now. So share screen, and that's annoying. Huh. Or maybe not. Okay, so now you guys see this screen here, and now if I go here, I'm assuming you see this. I hope you see this. And now I have to go and find and open the chat again. Today I had to move to the other room here because they're working, so I don't have the double screen there. Just chat here. Okay, now I can see chat. Okay, view slideshow. Okay, I'm assuming people can see this. Let me know in the chat. Can people see this? Now good. Okay, very good. Okay. So now we're going to talk about aggregation. So if you remember in the relational algebra, we were doing that gamma operator. So that's exactly what makes it into SQL. I mean, formally, it's doing the same thing. So this is kind of how that operates. So basically, we have aggregate functions, which again take a sequence of or a bag of single values, a bag of scalars, like just it's like a single row of values. I'm sorry, single column of values. And it will compute stuff like sum, average, count, min, max on that. Then it can also take in what's a star here, and the star stands for a set of tuples. Okay, so and it can count those. All right, so so here's kind of how aggregation. Here's a very simple example of how aggregation can work, and that is, let's say we have the table, like we sell a bar. A bar sells a beer at a certain price, and if we want to find the average price of Bud, what we do here is we basically we go over the sales relation, looking where it equals Bud, And then essentially what we're doing is we're projecting out price here. So price is being projected out. So that's turning into a column of values, all the price values for Bud. And then it's computing the average. Okay. So if you want to do, I mean, this doesn't make much sense in this kind of mathematically here, but if you wanted to do the distinct prices, so in other words, if you wanted to apply a distinct operator on that projection, of course, which wouldn't make any, well, I guess in this case, it would make sense because what we're doing here is now a count instead. So if we want to say how many distinct prices are there for Bud, then when we have distinct in there, what it will do is it will then, of course, eliminate duplicates on the projection. And then in this case, it'll just count out how many there were. I thought if it was doing average, that would be kind of a funny thing, but it's doing a count, so that actually makes sense. So null values are ignored in aggregation. So they never contribute to a sum, an average, or a count. They can never be the minimum or the maximum. So nulls just kind of get ignored. So it's kind of a special kind of way nulls again are being treated. But if they're all nulls, then the aggregate result is null. Winds up being null itself. Later today, we're going to talk a little bit more about nulls and exactly what they mean. Basically, this is just kind of a special case where if everything's null in aggregation, then the actual value is null. So that's that, except for count. So if you have a whole set of nulls, so it's just the way it is. So if you have a whole project out a whole they're all nulls, and you're doing the count, then it doesn't give null as a value. It doesn't give the result of null in that case gives a result of 0. Okay, so that's just a little thing to keep in mind. Okay, the effect of nulls. So what this right here is this would be select count of the full number of tuples. So this is the number of bars that sell Bud in the cells table, because well, each bar is going to be represented selling Bud. The count. So this is the count of all the. This is the count. This is doing the count over the tuples, and this is doing the count over the actual projection of the. So there's a distinction here in terms of what count is applied to. So star, when you see star, it always means a full tuple, all right? And it only makes sense for things like count, all right? I mean, PostgreSQL has some other ones where it makes sense for, but kind of like the aggregate operators that are always kind of there are count, average, sum, min, max. Those are, you're always getting those. So for average, sum, min, and max, having select max star doesn't make any sense, because it has to actually be a single value. But it can be a string or it can be a number, right? Because the max string will be the one that's the highest in the alphabetical, whatever the mapping stuff on the alphabetical lexicographical order. Okay, so again, well, the effects of null, yeah. So because there's nulls, I mean, you can wind up, yeah. So okay, so this is all really trivial until you start doing grouping. So then this brings in the gamma operator. So the way grouping works then is that you partition the tuples in the relation into a set of groups based on the grouping attribute, and then you compute the aggregation over those. Yeah, I'm sorry about the slides. It was kind of a rush with all the work going on here and everything. I didn't get a chance. I was going to upload it, but it was just it's kind of. I think it's finally done. I have to go check right now before break. But sorry. I'll during break I'll put them up. I'll put them up during the break. So. All right. So what do we? Okay. So what do we have here now? We have like a bar selling a beer at a certain price. Find the average price for each beer. All right. So over all the selling tuples, what is the average price of all the different beers? This is actually how you do it. So notice what you're doing. You have cells, right? So cells has bar, beer, and price. And when we say group by beer, however many beers there are represented in this table, it's going to define that many groups. All right. So it's going to partition. So when I say partition in a mathematical sense, what a partition is, it's a way that you kind of take a set of, or in this case, a bag of values of tuples in this case. And what you do is you assign them to one and only one group. That's what or in a partition, when you do a partition in mathematics, a partition, you wind up having a number of sets, and those sets are all disjoint, but they're complete in the sense that everything gets assigned to them. So everything under the, that the partition is being applied to will find its way into one of the sets and only one of the sets. All right, so that's what a partition is. So grouping is just a partition. It's the same kind of notion. It's a partition of a bag in SQL. All right, so it does this partition based on the, the beer, and then over that partition, it can then pluck out the price. It can do a projection over a partition for a particular beer, and then it can compute the average price. So I hope that makes sense. I mean, it's a lot of words I use there, but that's kind of what's going on here. So we'll play around with this a little bit just to kind of get some more intuition. All right, so in an aggregation, if any aggregation is used, then each element of the select list must be either aggregated or an attribute in the group by list. Okay, so this is where a common mistake is made. So this right here, this you'll see this quite a bit, and we have to understand, why is this illegal SQL? Why is this problematic? So we say select bar and the minimum price. So we want to know what is the minimum price for each bar, where the beer is bud. Okay, so I think what we're looking for right here is we're looking for, find the bar that sells bud the cheapest. All right, find the bar that sells bud the cheapest. And somebody might think, well, okay, I'll project out bar and then I'll like project out the minimum price. But this actually makes no sense, because you always have to have, either when you're doing aggregation, every attribute in the select clause either needs to be the subject of a aggregate operator, in this case min, or it needs to be in a group by clause. And this bar is not in a group by clause. So this actually just breaks down, and SQL just kind of, maybe we'll kind of put this thing through and we'll see what PostgreSQL says as a complaint, but it won't like it. I hope people can understand why, because again, in an if aggregation is used, then each element of the select list must either be aggregated, that is having an aggregation operator applied to it, or an attribute on a group by list. And this bar right here is not either, so therefore it's a no-no. All right, so it's illegal. So we'll try to get some intuition about that. Now, we can also do something here that is, again, syntactic sugar, but it in practice it leads to great speed ups, because if you have a having clause, you don't necessarily need to have one of these. You can do this as a subquery, but having a having clause makes things much more direct and much more efficient. But let's talk about what a having clause is. So the having clause might follow a group by, and what a having is, it's a condition that applies to the group, to the actual group. So a very common way what you'll see here is you'll say, like, I will only want, like, okay, so having, like, where the count is greater than, so here let's just follow this example here. Okay, from cells and beers, find the average price of those beers that are served in at least 3 bars or manufactured by Pete. Okay, so this is where having it. So if I just let's make this a little bit simpler here and just say we want the average price of beers. We want the average price for each beer if the beer is sold by 3 or more bars, right? So what that is, that's basically saying that when we do the grouping on the beer, the having puts a condition on the actual group. And in this case, it's saying that the bar, having the count bar, is greater than or equal to 3. Okay, this could also be a star here. So you could have a star here as well. It would achieve the same thing. So again, what the having does is it's usually a count. And what it does is it basically says, all right, I'm only going to do this calculation for the groups that meet the having clause. All right, and that's why it's more efficient, because if you have a tight condition here, then what it does is it reduces the number of groups that you actually have to compute the aggregation operator over. Right. So that's this additional thing down here is just another or or their manufacturer. It's kind of an odd query, but that's what having does. So the requirement of havings is anything goes into a subquery. So anything can go into a subquery. So this subquery here can just be whatever. It's arbitrary. Outside subqueries may refer to attributes only if they are a grouping attribute or aggregated. Okay, so it just has to do with like you can't the having here. The having clause has to be either applying to the. It has to be something that you can compute over the group. All right, put it that way. Oh, here we are. So that's done. Okay, and now I lost the chat. Nice. Okay. Nice. Get my chat. Okay. I think what I want to do now is I want to go and do a little bit more of SQL before we actually go, because we're just going to after. So okay, we have some things we want to cover in SQL in like on the. Let me just write them down here. Is that we want to do aggregation. But I figure what I'll do is I'll also go into a little bit more SQL. And because we might as well. All right, slide view slash. Because we're going to do all this, we're going to play around with all this when we go through and do some actual SQL live. All right, so we're going to do aggregation, we're going to do having, and then we're going to do a bunch of other things. But let's just continue covering this before we go into this. We actually go and play with SQL. All right. So the null values. So tuples, yeah, they can have null values for one or more components. All right. So depending on the context, there's like basically there are. So, all right. So you guys can actually, so the chat is not invisible to you guys. I know that it gets blotted out, so you can't see like private messages, but let's see. See, I wish I had, maybe what I'll do over break is I'll actually move to a, let's see, message. No, it's in terminal. Wait a sec. Can you guys see this? Oh, you said, okay. I mean, I think what I'm going to try to do is, if those guys are done, which I think they might be, I'm going to try to move back to the main desk so I can have more than one screen. Can you guys see? Now it doesn't. Okay, now it doesn't. Very good. Okay, so let's just kind of muscle through here. Well, maybe let's see what the time is here. 54. Yeah, let's cover some of this. It's pretty straightforward. All right, so we know that null values. They come up because either, I mean, the two most usual cases of null values coming up is missing value. So we don't know. We know that okay, this bar has an address, but we just don't know what the address is. So it could be anything really, but we just put a null value in there. And then we would have something like inapplicable, and this has to do with, well, the value for the attribute is not even. Well, the person doesn't have that attribute because they're not, like in this case of a spouse, because they're not married. Or let's say that we have a person, we have like a we have email and it's represented as null, but that's kind of where there's an ambiguity. We have this person in our database and they have null as an email. Does that, now they might be, you might think, well, gosh, everybody has an email, but that's not true. Some people don't have an email address. So does the null there mean that that it's missing, or that it's just that they simply don't have it. They don't have an email. So, but then there's an inapplicable, which I guess actually is a little bit different because you have the notion of like a spouse or a person. I mean, it would be kind of a bad design if you had it that way, but it's possible you would. We'll come up. Actually, there's a lot of cases actually where. I mean, okay, so some people actually did a big analysis of what are the actual like subtle differences of where nulls are used. What do they really mean? And I think somebody came up with like 14 different semantics. But we'll see that it comes up a lot of different ways. So there's usually two common cases, but there's a lot of other cases. So there's a lot of cases of nulls. So like for instance, outer joins create nulls. So what do they really mean? It could be inapplicable. It could mean missing. We don't know. All right. So, but anyways, SQL is kind of nice in the sense that it doesn't make any, it's just going to say we're going to treat null values as null values. And how do we treat null values? Well, null values actually are, null values are a way that we represent a three-valued logic. So basically things are true, false, or unknown when you start like working with null values. So if I say something like, let's say I have a null value in for the bar's address, and I say that the bar's address equals, I have a condition in SQL that says the bar's address equals 34 State Street. All right. Now, when I come to a bar that we have an address for and it's not 32 State Street, we can say definitively that's false. If we come to a bar that has 32 State Street as the address, we can say definitively that condition is true. If we come to one that has a value for null for the address, all we can say is it's unknown whether or not that tuple matches that particular address. Okay, so the actual condition in an SQL query winds up yielding a value of true or false or unknown. But we only report answers. We only report answers to the query that are, we only report tuples for the query where all the conditions are true, okay, not unknown. So that's kind of like how it goes. So we need a way to combine all these things. So comparing any value, including null with itself, yields null or unknown, okay? A tuple where the query answer is, a tuple is in a query answer if and only if the where clause is true, it's not false, and it's not unknown. So here's kind of how you can think of it this way. I'm not really sure how useful it is to think of that. I would just kind of more do it as a table. But basically, you could think of this. You could say true is the value of 1, false is the value of 0, and unknown has the value of 1/2. And then and does a min over those. So that would mean that if we have true and unknown, that'd be like, well, it would be 1/2. It'd be unknown. So if I have true and unknown, I get unknown. But if I have or, true or unknown, then I get the max, so I get true. So true or unknown, combine those together, you get true. And then not unknown is unknown, not true is false, not false is true. Okay, so you can kind of compute a whole way in which you can kind of do you can compose expressions, and then ultimately you're going to it's going to either result in true, false, or unknown for the truth value of an expression. Right. So this is an example right here. So what is true and false or not? So you can kind of compute this kind of bottom up, and you can see that the full answer to this thing is unknown. Right. True and false or not unknown. Okay. False or not unknown. That winds up being unknown. And then true and unknown is unknown. So it winds up being unknown. All right. And this explains that example we had when we were talking about price greater than or less than 2 or greater than or equal to $2. That's the reason why that works is because the price, if we have right here, we have Joe's selling bud for null, then is the price under 2? Well, it's unknown. Is the price over or greater than 2? Well, it's unknown. Unknown or unknown equals unknown. And this is the reason why, in this case here, the Joe's bar would not be a part of the answer, right? So law of the excluded middle. There's a lot of logic properties that do not. So basically, in logic, we basically have P or not P is true, but that's not true if P is unknown. Okay, so the law of the excluded middle doesn't work in this three-valued logic, right? All right, now this is the outer join here. We'll maybe talk a little bit. Okay, we already defined what an outer join was in relational algebra, but then if we look actually how outer join works in SQL, we'll see, and we'll practice with this when we get to it. We'll see right here that what this allows us to do is to put natural in front of outer, or we can have it as a theta. So we have this on, and we can say the full left or right. So we'll kind of look at those examples. All right, so let's see here. What are we looking for in terms of time here? Yeah, 11. So what we'll do is let's just take a break, and then we're going to come back. We're going to finish up this SQL discussion, And then we're going to go in and we're going to hop around and kind of play with it so we get a little bit of intuition about how it really works. So let's get back at 15 after, and I'll pause the recording here. I guess I first have to stop share, and then I will pause. And I will share screen. Okay, finally. Sorry about that. Okay, so I'm back at my desk, thankfully. Okay, so let's continue here. And what we got is database modifications. Okay, so yeah, so it's pretty clear that we want to be able to modify the data. We have to get the data in there somehow. So the way SQL does this is it has basically, it's usually what's called the IDM, or insert, update, and delete are the different types of queries, update queries that you can put into, or modification queries that you can put into SQL. So I think maybe you guys have seen these things, but basically you have something like insert. So insert into relation and then like a list of values. So this is kind of the literal way in which you do the insert. So you could insert into likes, Sally, Bud. So yeah, you want to usually specify in the insert, you want to actually put into the actual, when you specify the table likes here, you want to actually put in the names of the attributes. You don't have to do this, strictly speaking, but it's definitely good practice, because then what it'll do is it'll line up that the Bud is the beer and Sally is the drinker. Okay. You can get into trouble if you leave off this this heading. Now that we can also have default values, and the default values get put into the actual create table. So you put in something like this. You can say the address of Sesame Street is a default value. So if you, in other words, if you insert now and you don't specify address, it'll get this default. All right. So likewise, so if you see here, we put in the drinker Sally, then it'll default null to the phone number, and the address will be Sesame Street. All right. So you can also do this, and this is very, very common operation. Insert into, and then you name the table. And then you have a subquery that actually goes and from other tables populates that table. This is very, very common in what's called data exchange. So it's a very common use case in SQL, that what you wind up having is you wind up having a lot of data that gets gathered either through like scraping websites, or it gets added because it's a third-party database gets brought in. And what you want to do is you're trying to build up a database of the company's specific domain or operations. And so a lot of times what you'll do is when you grab off of other tables, you bring in these tables that are kind of like import data. You're extracting data from those tables. A lot of times what you do is you populate the tables of your database with these insert into and then a subquery, which actually goes off the source data and then manipulates it, modifies it via SQL, and shoves it into your database. Okay, so this insertion via subquery is very, very common. All right. So yeah, this is kind of like a toy example here from the. So this is the idea of like potential buddies. That is, if they frequent the same bar and they like the same drink, I guess, or something, but they're not the same drinker, then you could like put them into that table. But it's a little silly. Okay, then we have deletion, and delete just does what you think it would do. It deletes. It deletes tuples that meet the where clause. All right. So yeah, deletion. It's always a little bit dangerous to do deletion, but well, I mean, if you're doing if you properly checkpoint your database. So essentially, when I say checkpoint your database, means that you take a database, now you know you're going to do a bunch of deletions and modifications to it. You can do that under a transaction,
where you don't, not until you commit the transaction does it actually take hold in the database. But more importantly, you always want to have the database checkpointed in time. So if you need to go back and rebuild it from like, from earlier, that you can do that. The integration of Git-like technology or like version controlling in databases is still a little bit incomplete, but there's a lot of industrial activity around it. There's a tool called DB2 that purports to basically do it's like the Git for databases, but it's a little bit of a tricky thing because the models are a bit different. It's not just a file. The database is not just a file, and this interacts. This also interacts with transactions, which is something we're going to cover a little bit later. All right, can you add attributes to a relation? Yes, that's now that we're not going to talk about that today right now, but that's called, you do that via the alter command. So you can add column to a database table. And then likewise, you can remove attributes from the table, and that has kind of specific means. Now those are actually very nice spam bar. Those are very, like, we structurally change the database. So those are usually kind of what gets counted or called a schema evolution. And those are usually very, very tricky and need to be you need to be very careful about those. But again, with good checkpointing, you never lose your data, right? You always checkpoint your data. You always take a dump of the database so that you can always reconstitute it. So anyways, but yeah, you can alter the actual tables of the database as well. But we're not going to cover that right now. All right, so deletion, delete from, okay. So you delete the fact that Sally likes Bud, all right? Delete all the tables. So you can just delete from and then delete all the tables because everything is gonna, it's gonna go through everything. It's like doing select star, but it's doing a delete. Delete some of the tables. Okay, so this is a little bit something where you have to understand. There's a little bit of an intricacy around deletions, around the semantics of delete and how it actually works. The thing that you don't ever want to have in like databases is just kind of arbitrary choice, like where like something like if I say this, so if we basically say something like this, we want to delete from beers, delete from beers all the beers for which there is another beer by the same manufacturer. So this is basically doing is saying that, well, we want to slim the thing down, so we only want to have one beer for each manufacturer. Okay, so this is kind of silly though, because we have like 3 beers that are like under Anheuser-Busch or something, that they have that manufacturer, and we want to delete 2 out of the 3. Now that's an exact case where you're forcing the database then to make some kind of arbitrary choice, and it doesn't want to do that because we want to have everything kind of definitional, so we can kind of always determine semantically what we meant. So that's this kind of example here. So it deletes from beers where there exists another beer from the same manufacturer but a different name. Okay. So what does this do? What are the semantics of deletion here? So let's say that this Anheuser-Busch only makes Bud and Bud Light. Suppose we come first to the tuple for Bud, then we delete Bud, and then when we come to the one for Bud Light, does that mean that it's going to be true then? Or I mean, is that going to mean that we delete Bud Light? I'm sorry, that we don't delete Bud Light because we've already deleted Bud. So this is not actually the way it works. So this is the way deletion actually works under the hood. It works in 2 stages. First, what it does, it goes through now without deleting anything, it goes through the tables and it marks all the tuples for which the where condition is satisfied, right? So it marks them all. And then those ones that get marked, those are the ones that it then goes in as a secondary process and does the deletion of, okay? So in this case here, it's gonna basically, it's gonna delete everything. That's what it's gonna do. It's gonna go mark through and it's gonna delete everything. So it's not gonna retain anything under Anheuser-Busch. So it's going to be a little problematic. But that's the semantics. So the semantics is that you never do a deletion. You first do a first pass through the database and mark what's going to be deleted, and then you go through and you actually do the deletion. That's the key takeaway there. Right. So I'm going to squash here and see if I got any questions. All right. Okay, so now updates is the last thing. So this is basically giving us that full kind of CRUD capability, create, update, and delete. So the update part, what it does is basically you say that you name update the relation, and then you say set, and then the list of assignments, and then a condition. So this is right here. So for the drinkers of Fred, we can set the phone number to that particular phone number, right? And that's how updates work. So updating several tuples, yeah, sure, you can update, you can update many tuples at once. And that reaches the end of that. So, okay. So we've okay, I'll stop sharing. Or I should have stopped sharing. But the thing is I lost my chat. That kind of annoys. So bring back the chat. See if there's any questions there. And then what we want to do is we want to go to like an actual SQL screen so we can kind of play around with some of this stuff. All right, so share screen. Okay. Yes, we're going to share this screen. Desktop 2. And then what I'm going to do, I can't this screen nothing. I'm going to go here. No. Stop share. Stop share. And then share screen again. And then that really bugs. Fine. It's not letting me whiteboard. No. I don't know why, but it's not letting me do that. All right. But it's letting me do this, I suppose. So you guys can, okay, one sec. I need to open up another chat here. All right. So I take it you guys can see this SQL. Can you guys can see? Sure, I'm pretty sure you guys can see now my terminal here. So let's see, what are we gonna do? Good. Okay. So so I think the database I call this thing. I think I called it play. Yeah. Let's see here. So let's see the tables we have. All right, we have R and S. Okay, so this is actually what I did over here. I created a table R with attribute A and B as attributes, they're both integers, and then the table S is with B and C here. And then notice here I'm doing these inserts here. So this is kind of a nice thing to see that you can do. You can actually, you'll see this happen quite a lot. So I'll say something like this. I'll say insert into R. Sorry. I don't know if you guys can see that there. Insert into R. And then what, okay, now, like I said, what I should be doing is this, because I told you guys you should be doing this. So R, I say A, B, okay? So that's basically lining up the attributes. And now what I can do is actually I can put in here a set of tuples, which is kind of nice. So I say 5, 7, 11, 2, etc. So with this is kind of a shorthand thing. So a lot of times you'll do, you know, if we're in complicated little examples, you can do it this way. So I'll just copy that, and then I'll go down here and I'll paste it in. It doesn't like that. Why doesn't it like that? Because there's not because I missed a comma. Now, okay, so let's do a select star from R. And I had some stuff in there from before, but this is the full R. And as you can see, it's under set semantic. I'm sorry, it's under bag semantics, as we see 1, 2 is repeating itself, right? Okay, so let's do a full join here. Okay, that was R, and then let's look at S as well. So let's select star from S. Oh, and I only have two tuples, 2 and 3, but that'll be good. This will be kind of good for us to show. So now, so 2 and 3 on B. So it'll join there and there, and it'll join there, there, and there. So it'll join a lot of these will join, but there's going to also be a lot that are not going to join, like 11 and 5 are not going to join. So let's just do our outer join here. Okay. So the outer join here then is the syntax is basically R as X, and we're doing a full outer join. Let's just do a left outer join because that is done. A left outer join. So R left outer join with S, and I'm just doing an aliasing here. I'm aliasing them. I don't know if I need to do that, but let's see. What it's like. Do I need to alias? So aliasing, what that means, it means when you say that, like, he basically says as X. That's like introducing. Excuse me. That's like introducing a tuple variable, right? Just like from the straight tuple calculus. Anyways, there we go. So what this has done is then it's padded with nulls. So the 5, 7 didn't match. Anything on a 3 didn't match because there's no 3 for B in S, right? But the other ones did match through. So that's computing this full left join. And then let's see what else we get here. If I do, yeah, so that's that. I'm just kind of curious here. Do I need to alias? So if I say as X, I can just say that, get rid of that, get rid of that, and then just say RB, sorry, SB. Yeah, so that works too. So you don't need to alias. It's maybe good practice. I tend to alias things with X and Y. That's those become my tuple variables. X, Y, Z, or X1, X2, X3, X4, up to something depending. All right, so that's the convention I use at least. Expect it to be 2B columns. Why is that? Okay, the reason why that is because this is a theta join. This is not a natural join. Let's see if we can get like the natural join. The natural, since they are both called B here. That's so that actually that squashed down that B, because now we're doing it as a natural join, right? Natural outer join. Yeah. So I mean, let me just add something else in here for S. Let's have it so that S something in S doesn't make it through. So I'll just say, well, basically just take this guy right here. And I'll put it in there, and I'll basically call this S. And I'll put this up at like 56. No, I'll put this at 23. All right, so that's a left outer join, natural left outer join, but let's also do a natural full outer join. And when I do the full outer join, this means that funny 23 value, 23.3 should make it in now, and it does. So it's coming in as the interesting. Okay, so it does a natural join. It puts B first. Okay, I did not know that. But anyway, it does. Okay, it makes it. So the fact that PostgreSQL does that, like, look when it's doing the natural join here, it's shoving. These guys right here made sense because they just kind of like, line them up. But now that we're doing natural join, it puts that forward. Now that's the kind of behavior that I don't think that's in the standard, in SQL standard. I'm not sure, it might be, but I haven't noticed it before. But the thing is, that's the kind of thing that if you rely on that for some silly reason, then you're hurting the portability of your code to go over to like MySQL or SQLite or something, right? Because I don't know, we can see if SQL, I can determine if SQLite does this too, but it might have a slightly different syntax. All right, is there any questions? Left. Well, it doesn't. No, I'm not really sure about that because I think it's just based on the natural join, because otherwise it would have done that here, right? That's actually just kind of strange here. This is even stranger here because it's actually repeating B, which is kind of odd, to say the least. Like, what's the semantics of that? I mean, SQL is a little bit sloppy-doppy. But like so for instance, if it's going to want you to, I mean, you got to be select star. So a lot of times with SQL, like it'll do funny stuff like this, where it's actually having B and B here, which means that if you were taking this right here and you were trying to insert this into any other, like you were using this and then you're doing that insert subquery thing that I was talking about, then the fact that you're getting two attributes here of the same name is probably going to cause an error at that point, regardless. I wonder if I can do this as a subquery. Anyways, I mean, so a lot of times when you look at these things, you say, I wonder what would happen if I did that. Then usually with programming stuff, if you sit there and you say, I wonder what would happen if I did that, and then you don't go look, don't do an internet search or anything. Just do whatever it is, right? Because you can empirically determine how it behaves. So it's just kind of that notion of kind of empirical programming is what you would call it. Okay, so let's just do a little bit of aggregation stuff too. So select star from what's our probably our. Okay, so if I say this, let's say that we have those. What do we have? 1, 2, 3, 4 ones, 2 2s, a 5, and an 11. So if I group on A, and I want to do like the average B, if I group on A, let's just so select A, and then I want to get the average B from R. Okay, this right here, this should bomb. I hope that everybody understands. This is going to bomb because it's going to complain about A not. It's going to complain about A not either not being grouped on or not being under an aggregation operator. Okay, so it says A must appear in group by clause or must be used in aggregate. Yeah, that's pretty much what I said. Right? So that's not that. It'll bomb on that. But if we do this from R and then group by A, so it's going to partition the tuples into based on A. So it's going to put these 4 tuples here into 1, and then it's going to put these 2 into 2. This 1 into 5 and this 1 into 11, right? So all right, so that's that right there. But let's just count up how many there are. So just to count star. All right, so if I do a count star here, what is that going to do? All right, so this basically it right. Okay, so this is basically this is telling us that in that group 1, there's 4 tuples. In the group 2, with the group 2, there's going to be 2 tuples, 5, 1, and 11 as well, right? So this should all make sense. But what happens if I do this? It's kind of a subtle difference. Count of the B's. So this is how many B's are there. And now actually it's the same thing, right? It's the same thing. But if I then say, because that's how many B's are appearing, not how many distinct B's are appearing. But if I was to do this, now we're talking like, okay, this is how many distinct ones there are, right? So I hope these see the difference between these 3, like this one here. Well, that was just the count of the tuples. This is the count of the B's, like how many B's are there, which is the same as the count of the tuples. And then let's see, let's work in a null value here. Let me put in a null value for just call this a null here. What is this going to do for us? One sec. I'll take a gander. Did I just do what I know? All right, so now we have that. So now we're going to have 5 members of 1, right? Yep, there's 5 members of 1. And how many, but now how many B's are there here? Now, how many B's are there going to be in that group 1? Now there are 4, because it's a null. So you see how the aggregate operator it skipped that null value. Okay, it's like this is like little. I mean, do you need to know all these subtleties? No, not necessarily. but sometimes they'll come up and they'll bite you. So it's like when you get this, I hope you see that with these kind of little things. I mean, it's good to have a good basis in it because then you understand why you can control things a bit better with these things. Let's do a halving here. I only want to deal with groups that have two or more. All right, so right here. Okay, fine. I only want to deal with them that have from group by a having count star greater than or equal to 2. Okay, see now the 11 and the 5 are now plucked out because they don't have those groups aren't big enough to make it into the result. All right, I hope that's clear. All right. So what else did we have? We had, okay, is there anything else that anybody wants me to go over here just kind of as I'm doing this? Because otherwise I want to move on and quickly tackle something that's yeah, that I'm gonna do. Let's see, I'm gonna do. It's called recursion, and once we do this, then we're gonna be in really good shape in terms of the timing of the course. So we're gonna have some nice wiggle room to. We're gonna, yeah, it'll be great to get this covered today. But I will answer any questions if people want to put them up there. Let me see, one second. I just want to bring up this recursion thing. All right, first I'll show the slides, which are kind of so-so. Or maybe it's better that, no, I'll do the slides. No, I'm not gonna do the slides, not quite yet. Instead what I'm gonna do is I'm gonna go to the camera. One second. Where are you? I don't, oh, there it is. All right, so I'm assuming you guys can see this. All right. All right. Somebody put something in the chat if this wants to do. All right. So okay, now I'm feeling a little bit nervous, so I'll get this done. All right. So what's a graph? Graph is like in math, like it's the set of vertices and a set of edges, right? That's a graph. Can we represent a graph in a relational database? Does a relational database have the power to represent a graph? And the answer is yes. Two tables, actually one table, but let's say two tables. One table is going to be V, which is a one-place table. And the other one is E, which has the attributes from to. All right, I'll just call this ID here. So that there's for key there for from to. Right. So this is a directed graph, right? This is a directed graph where node 1. Okay, so let's represent the following graph: 1, 2, 3. I'll take this one. 4, and then 5. 5 is just isolated. I was a little bit low on this, so I'll make it point to 6. Okay, so this is a graph, right? People see that? We got a graph of it's not a connected graph, but we like to say what are the nodes that are reachable from node number 1. Okay. Now, if I basically then the actual state of the table is that this is the state of the table from if you want to get kind of fancy here, you can have this a cycle from 2, and it's going to be 1 2 2 3 3 1 3 4 5 6. Okay, got it all? Everybody got that? All right, so the question is the following. I want the answer to the query in relational algebra. I want you to answer the query in relational algebra of give me all the nodes that are reachable from node number 1. Okay. Can you express that in relational algebra? Can you express that in relational algebra? Do people understand the question I'm asking? Give me the nodes. Oh, hold on. Sorry. Can you see there now? Good. Person says, I get the question, but I don't think it can express that. Perfect. Good answer. That is exactly true. Now, if I say a different query, I say, give me the nodes that are reachable from 1 within 7 hops, or within, let's just say within 2 hops. Can you express that in a relational algebra? Give me all the nodes that can be reached by node number 1. And we only table we're using is E. All right. Give me all the nodes that can be reached from node 1 in 2 hops. Can we do that in relational algebra? Two hops. Okay. Okay, yeah, it is possible. Let's just quickly do it. From 2 here, if I say the following, I say, I'm not sure if people can see this here. If I say E, I'll do a theta join E prime with the understanding that's just a copy of E, and I'll say that E dot 2 equals E prime dot from. Okay. So what that's doing is it's basically forcing equality of the 2 to the from. So that would give us something like 1 2. So in this result here, we would have 1 2 2 3. That would make it in. Likewise, we would have 2 3 3 1. Right. Those would make it into that right there. And let's just make it. All right. Let's just do another hop here, and I'm going to say E prime 2 equals E double prime dot from. And now I'm going to project the E double prime dot 2. Right. Now, and then I'm also going to say, I'm sorry, I'm going to also say, inside here I have to say it, select E dot from equals 1. Right. That should give us, let's do a double hop. People see that? All right, let's put a let's use recursion in the relational algebra. All right, so let me show you how I'm going to do that. I'm going to say that I'm going to define R, which is called reachable from 2. All right, it's going to have from and 2. So E, the basic underlying graph, that's in R, right? So if from 1 to 2, that means that 1 2 is also going to be in R because 2 is reachable from 1. Okay, we cannot see. Can you guys see now? Is it too bright or too light, or is it the shading? Can you guys see now? It's okay. Maybe not ideal, but okay. Let's see what's the time. I think we're gonna have time. Let me just make it a little bit better. Turn off the light. Okay. All right. So this is a recursive definition of R. Because it's basically saying this is the base case where it just takes in the basic relation of the edges. And this one right here, what it does, it says, okay, take that in and now recursively apply it. So R is being defined recursively here because now R is being used in its own definition. So this is the recursive case here. And so what it basically says is it says now it's also going to be in R if it's in R already, and then we can reach it with one more hop. So this is always giving us the next hop. Okay. So what this does right here is this right here will define R, and if you want to like kind of calculate R, you do what's called a fixed point operation. And so what a fixed point operation will do is that it will basically, if we take this base relation here, what R is going to wind up doing, what R is going to wind up being, first R is going to equal this. Let's make it a little bit sad, but then we can calculate R here. So actually, maybe I'll waste more paper here. I'll just calculate R from this. So R, first of all, R is going to, in the first step, R is going to equal 1, 2, 2, 3, 3, 1, 3, 4, and 5, 6. Right? That's in the very first step. So this is what R equals on our first step. Right? Now I can, because the way R is defined recursively, I can now apply another step where I'm going to join R, itself with E again to kind of reach one more step further. So if I do that, then what that's going to basically say, it's going to say, oh, okay, if I can, here's R. If I can get from 1 to 2, I can also get from 2 to 3 here. So I'm going to add in the next couple, 1, 3. I hope people see that, because here's R, and I'm joining R with E, and I'm joining it on 2 here. 2 equals 2. Then that means that 1 can reach 3. 1 can reach can reach 3. All right. So 1, 3 is going to be in there. What else is going to be in there? 1, 1 is going to be in there, I believe. Let's see. One second. I'm getting ahead of myself there. Sorry. So if 1 can go to 2 and then 2 can go to 3, that means 1 can go to 3. If 2 can go to 3 and 3 can go to 1, that means 2 can go to 1. If let's see here, if we can, kind of mindlessly go through this. If 3 can go to 1 and 1 can go to 2, 3 can go to 2. If 3 can go to 4, well, 4 can't go into anything. But if 3 can go to 1, and 1 can go to 2, 3 can go to 2. I already got that one. Okay, so these in the next step, these are the 3 ones that are added further. Okay. Okay, so that's the second step, but R is getting bigger and bigger, right? R is getting bigger and bigger, and now we can join it again with E here, and hopefully now we'll be done. Let's see. If 1 can go to 3 and 3 can go to 1, that means 1 can go to 1. Sorry, 1 can go to 1. If 2 can go to 1 and 1 can go to 2, that means 2 can go to 2. Okay. And then if 3 can go to 2 and 2 can go to 3, 3 can go to 3. And then, well, I think actually if 1 can go to 3 and 3 can go to 4, that 1 can go to 4. If 2 can go to 1, I'm sorry, 2 can go, if 2 can go to 3 and 3 can go to 4, then 2 can go to 4. Okay, anyways, the thing is that what'll happen here, sorry, it was maybe a little bit too big. What'll happen here is that this will terminate. This will finish at one point, okay? And it'll finish, and when it finishes, it'll say that, sure, can we get from 1 to 4? Yes. Can we get from 2 to 4? Yes. Can we get to 3 to 4? Yes. Can we get to 4 to 1? No. Can we get from 3 to 2? Yes. 3 to 1. It's going to compute all of those, all right? It's going to, but notice here, that once it computes all that, once it does all that fixed point, it does this out to completion. Once it does this out to completion, Never will it be the case that from 1 you can get to 6 or 1 you can get to 5. All right. So it's basically doing the connected components of the. It's calculating through recursion. It's calculating the what's reachable. All right. Now, what we'll notice here is that we can do the same thing. So we've shown it in relation to algebra. I hope you guys understand the concept. And then what you'll see here, let's just share screen. I don't think I'm gonna have I don't think I'm gonna have the chance today to show you this in SQL, but I think I'll develop that and send it out as a message. Just showing you the SQL that does the graph reachability. But I don't think I have the time to actually type it into the terminal right now. Sounds expensive. Well, actually, it is. Expensive. All right. So there's actually a lot of optimizations. There was a real effort at one point to really optimize these recursive queries. But the truth is, actually, my experience with recursion in a practical sense is that you actually don't. I mean, it's kind of a little bit disappointing, but you don't actually do. I'll talk about that a little bit later. But yeah, there are some performance issues. One of the questions people might have is, does anybody ever use this? Does this ever make any difference in the world? I mean, does anybody actually use recursion? I mean, is it practical? I mean, is it practical to know kind of like what is part of what is part of what is part of what, without end? And the answer is yes, it's very practical. So recursion gets used usually. Maybe I'll talk when we talk about functions at one point. I think I'll say a little bit more about how you actually do recursion. It's a tricky thing because you're right. Your intuition is very, very good. I think that this is really good comments because there are performance issues, absolutely. But anyways, let me see here. Share. I'll share this one. All right. So SQL 1999 included this kind of with recursive stuff that looks like the rules. SQL. Okay, anyways, here. This just we'll look right here. Oh, here we are. So this I think this might work inside of PostgreSQL. That's what I'm a little bit uncertain of. Is actually if I type this into PostgreSQL, will it work? Because the syntax always is a little bit different for each one of them. But the idea here is this: is that you have the with clause, and I forget what they call these things. Generally, I don't like it when people do this, when they have a with and they start defining stuff in it, and then they have their SQL at the bottom. I mean, you need it for recursion, but I've seen people do it where they've done it like, but I mean, I haven't seen students. I've seen people in the industry do this, and they're overusing it a little bit. It's nice to kind of just have things in this one block SQL sometimes. But anyways, this idea here is that what you can do is you can have a with clause, and then you can kind of have you can define these names, or you can have things. So you can have something like this. You can have ultimately you can have like with, and then you set a variable, and then you include that variable in your query. This is my pet peeve. I don't like when people do that. I think, why don't you just put the variable inside the query? Thank you very much. I mean, okay, maybe there's good reasons, but a lot of times there aren't good reasons, and it just leads to clutter. I'm anti-clutter. Anyways, this right here is giving us the definition of R, or this reachability. So you say with recursive R, and then you're going to basically select the from and to from the underlying graph here. That's the base case there. And then you're doing a union, and then you'll see, and then you're doing union, and you have to make sure you don't do this. Don't do that, because that makes it so it doesn't terminate. All right. Union, because it's set semantics here, and then it's going to then use R with inside itself here and do the join. So I hope that people can see that. I mean, the syntax might maybe looks a little bit jarring, or kind of, it looks big and kind of weird, but just really go through this and understand the syntax exactly. You have a question on your lab 2 that we have to, lab 1 rather, I'm sorry, lab 1 where you have to do recursion. So you're going to have to kind of study how to specify these things. Anyways, once you have this recursive R here defined, then you can just use it in the query here. So select what are the things that are reachable from the node A. Okay, and that's what that does. That's recursion. So yeah, it's one of those things where you want to play around with it a little bit, and I think you'll get a chance to do that on Lab 1 to get an intuition. I guess what I should tell you people is that a lot of times the way you do recursion is you do it as a program and you grind it out and you put it into temporary. You don't put it, okay, not temporary tables necessarily, but you put it into you populate tables through the recursion so that everything is calculated at it's calculated before you get query time. So I mean, of course, the problem with that is that as you update things, you have to redo the calculation. But in a lot of cases, what's the basis of the recursion is static, so it's not changing in the world. If it's changing in the world, then yeah, you have to go back to actually computing recursion on the fly. But generally speaking, that you'll just kind of manually grind it out as a compilation process, at 2 o'clock in the morning or something. It just there's a lot of reasons to do it that way. A lot of reasons for efficiency to do it that way. So the comment about this seems expensive is the intuition was correct on that. But then again, for small databases, a lot of times everything is done so quickly. So all right. Anyways, this is for big databases. You want to do that kind of offline direct computation of recursive relation. So okay. If there are any questions, I have to kind of find my chat again. And I did complain. If I had to complain, I'm telling you right now, if I had to complain to them who run Zoom, is could you please keep the chat up as you Facebook. Yeah, the thing about Facebook's not using a relational database under the hood. They're using Cassandra, or at least they were. Whether or not Facebook really does, so there's the whole. By the way, I should maybe mention that there is the whole topic of what are called graph databases. I mean, I for me, it's like it's always good enough to if a relational database can represent graphs, that's good enough for me. But for efficiency's sake, there are certain particular query languages coming on the market that are really adapted to graphs. So I think that the one that Amazon is running is called Neptune. If people are interested, I haven't done any work with these things, but there are some specialized databases working around just the graph model. Now, with a graph, can you represent arbitrary relations? For the most part, I would have to answer that no. Relational databases are strictly speaking more expressive than graphs. Now, somebody might go and contest that, but there's a lot of things we can say about that. Well, you can represent it maybe in a graph, but you'll have kind of like a major blow up in the size of your queries, because if you just reify things in a graph, I mean, you could take a relation, you could just reify it in a graph. But then if you wanted to ask kind of important queries and having joins or aggregation and all that, where maybe in principle you could do it, but it would lead to some major blow up in the size of the query. I don't think an exponential blow up, but a high polynomial blow up. So yeah, but okay, guys, why don't we just leave it at that then? If there's any more questions, just type them in the chat. Otherwise, we'll conclude at this point here. All right, and I think we're going to actually kind of go into conceptual modeling on Thursday, so that's good. So we're going to be a little ahead of the game, but we'll make up for it later. Don't worry. Okay, I don't see any questions, so I guess with that we'll just conclude. I'll stop the share and I'll stop the record.